All right, gang. Time for the rest of Chapter 5 from our Carlton Adler and Ballack book. This is a continuation of a recorded version of the physics course that I teach at National General Hospital. Okay, and so we're finally getting to the X-ray tube. Okay, and so we've the talked about the schematic already. Um, I think I recorded the heat units lecture already, but I think the order might be reversed for the actual rollout of the course. I think we cover this first and then heat units, but I think on YouTube I've already recorded and uploaded heat units, and so this is appearing afterwards. Um, as far as the order of the recordings, might be off from the order that I present the class. So, okay, so draw. Now this is from the authors. Draw a complete dual focus cathode assembly. I think probably labeling a diagram of a modern X-ray tube, all the piece parts, and what their purpose is might be a little bit better than practicing your artistry. No one's going to ask you to draw a sketch on the registry. So what you can do is go on the internet and get unlabeled illustrations of an X-ray tube, or take those into Photoshop if they're labeled. Take them into Photoshop and white out the labeling, and then make that into a little flashcard for yourself for both the schematic and a model of the X-ray tube. I'd also recommend doing that for an image intensifier, knowing the piece parts of an image intensifier. What are the names of the pieces and what is their function? It's a good exercise for preparing for the equipment operation and quality control section of the exam. Okay. What are the piece parts called? What do they do inside whatever device you're diagramming? So, necessary characteristics of filament metals and construction. We do understand that we want a filament that's durable. We are going to push a lot of heat through this filament by means of pushing a robust current through it. So big current, tiny wire, you get a lot of heat generated. Okay, that heat is necessary for the thermionic emission, which I think we've talked about before, but we'll definitely mention again in this lecture when we're talking about the X-ray tube. But I believe thermionic emission was one of the goals for the X-ray schematic, was to create an available source of free electrons. That's what the thermionic emission will do. Okay. Select exposure factors and techniques that will extend tube life. That's in the heat units lecture. Draw a complete rotating anode assembly. Again, no one's going to ask you about your drawing skills and your artistry on the credentialing exam. So far more useful for you to correctly label a pre-existing illustration rather than spending your time drawing your own illustration. You knock yourself out if you have artistic ability and you want to draw this stuff. You're welcome to do so. But I think the more important skill set as far as preparing for the credentialing exam is identifying the parts from a pre-drawn illustration, like you'll find several examples on the internet. Okay. And then characteristics of anode targets. Basically, whatever makes for a good filament also makes for a good target anode. So, yeah, tungsten's involved, both cases. Function and design of a grid biased focusing cup. That's a special new re-engineering of the focusing cup that has come about in the digital age, so we can get a high frequency pulse X-ray beam, okay, like a machine gun X-ray beam. Explain the line focus principle, its effect on anode target design. Okay, so your rotating anode target and your stationary target typically invoke a beveled design with a target angle, which is the top angle looking at it from the side, If you drop a plumb line, the beveled surface intersects the plumb line at a target angle. Okay, and that's what they mean by the target angle. It's the top angle of the triangle. And I'll show you a diagram for those for that coming up when we talk about line focus principle. The line focus principle allows us to spread out electron bombardments across the surface of the anode while maintaining a small effective focal spot. Okay, and we'll show you how we do it. Basically, it's the hypotenuse of the triangle for the bombardment zone versus the short side of the right triangle for the effective focal spot. Okay, but we'll get there. The anode heel and its effect on primary beam intensity. Basically, the heel is part of the rotating anode. It's the outermost and posteriormost, farthest away from the cathode, so to speak. And it ends up reabsorbing part of the X-ray beam because it's made out of high density tungsten metal that's got a high atomic number. So the anode is the first victim to X-ray reabsorption, photoelectric effect. Okay. Production of off-focus radiation. The electron is a quantum object, and so it doesn't always go where we intend it to go. We intend it to go to the focal track and the focal spot, but sometimes it goes elsewhere. And so we got to explain what happens when it does go elsewhere. Okay. Rotating anode, induction motor, stator and rotor. So I've already described to you the stator and rotor and how we get an induction motor to work in the transformer lecture. And so we're just going to apply that to, let's tether the rotor part of the motor to the anode wheel. The rotor is going to be the axle of the anode wheel. And bing, bang, boom, we translate the rotational motion of the rotor to the wheel. Okay, not that hard. Now, why do we prefer a rotating anode? Is it an improvement to the design? Well, it takes a lot of work to convert to a rotating anode design, so there must be some reason for it. There must be some justification for it. And the justification is you can stack a lot more heat on a rotating anode than you can a stationary anode. So the heat capacity of the tube increases, and you can work the tube for longer exposures and bigger exposures before it overheats, or it's in risk of overheating. Okay. And then the construction of the envelope, they used to call it the glass envelope, but now they're making envelopes out of sheet metal. So they have to call it the envelope. And the protective housing, which is separate from the envelope. Okay, so how do we make X-rays? You might remember from the schematic lecture that we need a source of electrons. That's what the cathode filament and the filament circuit is for, is to boil off electrons at the filament via thermionic emission. So thermionic means you create ions by applying heat. And so most metals will do this. If you heat them up hot enough, they'll start to glow red. That red glow is electrons getting excited and then relaxing back down. If you keep heating it, the red will turn to orange, then to yellow, then to bright white. Okay? And then your filament will melt if you keep pushing it. So we want to stop at bright white. Okay? Maybe stopping at yellow. Okay? So we need a source of electrons. We need a means to accelerate them. That's the high voltage supplied by the X-ray circuit and the high voltage transformer. And then we need a target for them to slam into. Now the target, the atomic number of the target material, it determines the characteristic photon emissions that we get out of the target material. Tungsten has a characteristic emission of 69.5 keV, which is right in the middle of the diagnostic range, so that's very handy. and we basically get bonus X-rays if we use tungsten as a target. Okay, that is one of the reasons we're using tungsten as a target material. Okay. Vacuum is not necessary, but it's optimal. Okay. The vacuum is optimal because you can have a gassy X-ray tube, a slightly gassy, low pressure X-ray tube, and it'll still work. It's just you increase the efficiency of the electrons getting to the anode if there's no molecular impedance. So any air molecules inside the tube will collide with the electrons that are rocketing across from the cathode. Okay? And so by doing so, they won't intersect the target, the intended target. They'll intersect a target, the air molecules that you let get inside your tube. Now, so X-ray tubes can operate at vacuum or extremely low air pressure. If it's regular air pressure, let's say the envelope cracks and the vacuum's destroyed and you get regular air pressure in there, then the tube doesn't work anymore. There's too many air molecules and no electrons will effectively reach the anode. And so you do need either total vacuum or partial vacuum. Okay? And that's why I say it's optimal. A total vacuum is ideal, but you could still, and the Crookes tube that Rankine used was only partially vacuum evacuated. It wasn't a perfect vacuum like we can create today. So. And then the focusing cup. The focusing cup was a design enhancement. Coolidge definitely had it in his patent that you see on the wall of the classroom. But it confines the electron cloud to a small area so it doesn't spread out like a shotgun blast when you launch the X-rays over to the anode. Okay, so the focusing cup offers, in most cases, repulsive forces to keep the electrons basically in the bottom. The focusing cup is shaped kind of like a bathtub, and so stacking extra negative charges on the rim of the bathtub allows for the electron cloud to stay in the bathtub in a confined space. Okay. Coolidge was the first one, the most notable one, to improve on the original design of the Crookes tube, and the Coolidge tube featured tungsten wire and a hot cathode filament, just like a light bulb, and it featured a focusing cup, but I still believe it had a stationary anode at that time. It was later designs that they re-engineered the anode into a rotating anode. Okay. Not sure who came up with the rotating anode design. That would be interesting to look up. Okay. But here's our modern X-ray tube, very similar to the Coolidge tube that you see. So it's got the same basic components. It needs a cathode and an anode. The nuance, I guess, is that the anode rotates. That's the only difference between this and a Coolidge, an original 1911 patent Coolidge tube. Okay. The Coolidge tube might also have had a water-cooled anode. Some designs indicate that. So, all right. So your major piece parts: rotor and stator, armature, which is kind of like a shroud for the rotor. The bearings go in between the rotor axle and the armature. A positive potential wire coming off of the rectifier connects directly to the rotating anode. Negative potentials come in from the filament circuit, but later on the bridge from the negative terminal of the rectifier, okay, during an exposure. So then we surround the whole thing in a capsule typically made of glass, that envelope, but not always made of glass. Some of the modern designs are using sheet metal, steel, or aluminum or alloys to build X-ray tubes. Okay, we figured out we don't have to use glass. We can use a metal envelope, and that helps with filtrating the X-rays. Okay. A particular part of the envelope is called the window. It's not labeled here, but it's where the X-ray beam is coming out. In a glass envelope, the window portion of the envelope is thinner than the rest of the envelope. Okay? And that's so that the window and the glass envelope don't absorb as many X-rays. Okay? I don't know if that carries over to a metal envelope or not. Okay? Now the protective housing is not pictured here. It would go around all of this. The stator and the X-ray tube itself is inside the housing. The high voltage connections and the filament circuit connections also come into the housing. Okay, and there's a cathode and anode coupling that the housing brings in. Okay, so the housing starts as a cylinder, but it's got two exit points for the wires, usually on the back of the X-ray tube, facing back toward the crane. The electrons are excited at the filament once the filament gets hot enough. And then when the high voltage is applied, the huge positive charge that results on the anode pulls the electrons across at very high speed up to, I think, 3/4 of the speed of light, 2.5 times 10 to the 8th meters per second. All right, so our cathode assembly basically has two primary parts. Filament, which is usually dual filament, is primarily made out of tungsten in a coiled wire. And again, creating tungsten wire was a metallurgical process that was invented by William Coolidge. And so that's why he was able to patent the device, is because his hot tungsten coil filament was unique and his brainchild, and so he had a obligation to GE Corporation to file a patent so that they could reap the benefit of his design improvement. Okay. I'm pretty sure that patent has expired by now, and everyone is making a hot cathode filament with ductile tungsten wire. So patents are only good for about 7 years. So the second part of the cathode assembly is the focusing cup. The focusing cup also supplies a negative charge, but the whole point of the focusing cup, now not always does it supply a negative charge. That's one of the new re-engineerings. And I think I'm coming up to that slide. But traditionally, the focusing cup, if you supply it with a negative charge, it's bathtub shape. So the upper rim, remember, sharp radius of curvature, that's where charge seems to concentrate. So that upper rim of the bathtub, as indicated by the arrow there, is where the negative charges are going to appear to stack up, and effectively any excited electrons coming off the filament are effectively trapped in the bottom of the bathtub until they experience the pull of the high voltage that overrides the repulsive force supplied by the focusing cup. Okay. So there's usually 3 wires running into the filament. 2 of the wires go to the ends of the step-down transformer in the filament circuit. The middle wire is connected to the bridge. It's the bridge connection that is a fork in the circuit, so to speak, to connect back to the rectifier and the high voltage transformer. Okay. So the bridge connection is dead until the exposure switch is pressed, and then the bridge connection takes over the filament circuit. Okay. Typically, the filament circuit is low voltage operation until the moment of exposure. So heating up the filament is low voltage, high amperage. Okay. It's the high amperage that triggers the thermionic emission. Okay. So here we have a picture of a filament that's been removed from an X-ray tube, and you can see that both of those filaments effectively sit at the bottom of a bathtub. That's the focusing cup. Now, we actually don't use pure tungsten. And the reason is a thorium tungsten alloy has a higher melting point than just pure tungsten. And so I'm not sure when we figured this out, but the filament uses thoriated tungsten or thorium tungsten alloy because it can achieve a higher melting point, so we can push even more current through it, heat it up even hotter, and thus generate bigger clouds of electrons rather than if we just use plain tungsten. Okay. The melting point of tungsten by itself is pretty high already, but we can push that even higher with the presence of the thorium. And it's about 3,370 degrees Celsius, which is about 3/5 of the way to the surface of the sun. And so it's really, really hot. Yeah. Really, really hot. Okay. We want to heat the tungsten up. So just like at the blacksmith, when they heat up the iron or the steel, they put it in the forge, and the fire heats up the metal till it glows red, then it glows orange, then it glows yellow. Somewhere between orange and yellow, the metal starts to get soft like clay, and you can pound it into various shapes. In the same respect, tungsten, we don't heat it up because we want it to get soft necessarily. We heat it up because we want to excite the electrons on it. And so we heat it up to just below the melting point. It's glowing white hot, and lots of electrons are excited. Okay? And we'll use those excited orbital electrons to create the tube current. Okay? So why do we choose tungsten? Well, first of all, high melting point, difficult to vaporize. It doesn't like to boil. Okay? And doped with thorium to increase thermionic emission. Now, the way that it does that, oh look, Sir William Crookes. William Crookes discovered. Oh, that was thallium he discovered, not thorium. Whoops. Okay, maybe I need to remove that picture. Anyway, we dope it with thorium. Did he? I'll have to look that up and see who discovered thorium now. Okay, to raise its melting point and to add more valence electrons. Thorium has valence electrons as well, and they might be easier to liberate than tungsten electrons, so less energy. So the net result is we get more thermionic emission when we add in a little bit of thorium to our tungsten wire. Okay, rhenium and molybdenum are also good choices for filament metals. Thermionic emission. Okay, so I've explained it before at least twice, but again, you can see thermionic emission in this Edison light bulb right here, and that's actually carbonized bamboo filament that's giving us that soft orange glow. Okay, if you push more current through this, you'll definitely burn up that filament. Okay, Edison filaments were Edison bulbs typically had about somewhere around 11-12 hour shelf life in the first iterations of them. They got more and more efficient. They got extremely efficient when we swapped out carbonized bamboo for ductile tungsten wire, Mr. Coolidge. Okay, so remember, the tungsten filament wire was originally invented to improve the incandescent light bulb, not the X-ray tube. It just so happens that Mr. Coolidge was a genius, and he figured that you'd get a more robust X-ray tube with a hot cathode. And so he had already invented the improvement for the cathode filament. Now he just needs to transplant it from his Generation 2 light bulb to an X-ray tube, or a Crookes tube. Basically, re-engineer the Crookes tube to have a hot cathode filament featuring tungsten wire that only he knew how to make. So it was industry secret kind of stuff. So from 1911 to about 1920, the only company that could make hot cathode filament Coolidge tubes was GE. And so they developed almost a monopoly on making X-ray machines, at least the X-ray tube part of it. Okay? So that put them in a very powerful position, and that's why we still see General Electric making imaging equipment technology, because they have such a strong foothold in the marketplace. Okay? So when we heat up the wire by pushing excess current through it, those electrons in the orbital shells, they excite, they jump to higher energy levels. Okay, so it's not technically ionization until they leave permanently. So excited state it's definitely an elevated energy state from the ground state, but maybe not enough energy for the electron to completely leave the atom. Okay, because that would be ionization at that point. So excitation is the electrons that are at a higher energy state, but they're not they haven't passed the conduction threshold, so they can't leave. They have to relax back down. Okay? And so there's a sweet spot of how much current you push through to create excitation, but not necessarily ionization. Okay? The filament circuit is meant to get hot first before exposure begins. And so there's usually a lag between preparation and boost. If you mash it all down at once, you're going to experience that lag. It's about 1.5 seconds. You're allowing time, the circuit is allowing time for the filament to heat up, so we have an available electron cloud, but also for the rotating anode to get up to speed. We need that thing at about 3,000 RPMs or faster, okay? In order for it effectively to distribute the heat from the bombardment of the electrons. So here's a good diagram of the focusing cup. Focusing cup, again, is for optimal efficiency. It's not necessary. You could totally build an X-ray tube without a focusing cup. Just have a bare piece of coiled wire sticking out there into the middle of the tube. But that means your electron cloud is not going to be impeded and confined to a small space. And so we're getting repulsive forces from the focusing cup that keep the excited electrons down in the bathtub. It's only when we apply the high voltage that the electrons respond to an even greater force and accelerate across the tube. They're confined by the focusing cup until the high voltage generator and the exposure switch is turned on. Okay. Keeping the focusing cup keeping the thermionic cloud, or the space charge is how it's called, small, allows us to keep the focal spot small. If the focusing cup is not there or it's not working, your space charge, your electron cloud, is going to bloom, that is, spread out. And then when you apply the high voltage, you'll get bombardments all over the entire surface of the anode rather than a specific focal spot. Okay? So the focusing cup is fundamental to keep the focal spot small or confined to a small space on the target anode. Okay. Now, the space charge effect. Okay. This is kind of like the velvet rope at the exclusive club downtown. Okay. So there's a fire code, so to speak, for the space charge. The cloud becomes full of excited electrons. Those electrons are self-repulsive as well. And so let's say we've got 50 electrons in the cloud, and another electron decides it wants to become excited and jump into the cloud. But the cloud is full. It's got 50 electrons in it. So all 50 of those electrons are pushing back on the 51st electron, and it becomes harder and harder to push more electrons into the same confined space because of the repulsive forces and because the cloud is not allowed to grow and spread out. And so what that means is there's only so much thermionic emission you can generate. You get maximum cloud volume. We call that the saturation current, and it's about 5 amps of filament current. Okay, at about 5 amps of filament current, you get this threshold where you can't stuff any more electrons into the cloud. Okay, if you run lower filament currents, the capacity of the cloud is even less. Okay, and you can kind of see that on this chart. Okay, increasing kVp effectively increases the size of the cloud because the kVp is depopulating the cloud during the exposure. And so those electrons that are trying to get into the cloud, but they're being repulsed, as soon as the kilovoltage is applied, the cloud begins to vacate and depopulate with electrons. And so there's spaces for electrons, additional electrons to jump in and replace. But there is a maximum capacity to the space charge. You can't just set, well, let's just set 100 amps of filament current and then we'll get, 600 billion electrons. Wait, no, it doesn't. You just can't ramp it up to infinity. It doesn't just keep going and going and going. There's an upper threshold, and that's called the space charge limit. And that upper threshold appears because of the Coulomb repulsive force. Electrons in the cloud repel additional electrons from joining them. So if the cloud's full, you can't get any more. There's an upper number somewhere. It's not 50, but 50 million, 500,000. I'm not sure. I haven't counted the electrons in the space charge. But if you understand Coulomb's law, you understand why we get to a saturation current. All right, now this is the latest and greatest. This has come out since I've been an X-ray tech. And it really only made sense to add this once we got to digital image receptors. So this is called a grid bias tube. So what you can do with that focusing cup is you can alternate positive and negative charge through it. Okay? And so you still have a space charge at the bottom of the bathtub. When the focusing cup is negative, it's raining that charge in, but when you flip it to positive, it actually grounds out the filament current. And so you basically get, if you're making an exposure and the high voltage is on, but the focusing cup is constantly flipping, when the focusing cup is negative, you'll make X-rays. But when the focusing cup is positive, the positive focusing cup grounds out the available space charge, and you don't make X-rays because none of the electrons end up rocketing over to the anode because they have a faster pathway grounding out on the positive focusing cup. So what that means is, as fast as you can flip the polarity of the focusing cup, that's how many bursts of X-rays you can create per second. And so the frequency, if you connect it up to a high frequency AC wave, your focusing cup is going to give you a high frequency X-ray pulse like a machine gun. Okay. So what that does is it makes it so we can take pulsed fluoroscopy. Okay. It also works pretty handily with capacitor discharge unit, but the real benefit is in dose reductions in fluoro. Okay. Because you can sync up the pulses of the X-ray tube with, let's say you have software that can process 30 frames a second. And so you send bursts of X-ray at 30 hertz, 30 cycles per second, and that matches up with how fast your detector can process images. And so there's a dose savings to the patient because a continuous fluoroscopy beam is wasted on a digital receptor. It captures a data set and then it processes those. And so while it's processing the first data set, if you're continuing to expose the detector, it's basically ignoring that information. It's already captured in this 1/1000th of a second. It's captured, or 1/30th of a second. It's captured one set of data, then it turns the detector array off and downloads that data and sends it to the CPU of your computer. Then it turns on the detector again. Well, there's a fraction of a second there that the X-rays bombarding the detector are useless. And so you're dosing the patient but not capturing the information. So dose the patient in pulses in the same frequency as your detector reads out. If your detector can read out 30 images per second, then give it 30 pulses per second and you're not wasting any X-ray. You're capturing and converting 100% of that X-ray pulse to another image, a brand new image. Okay. We'll talk more about pulsed X-ray when we get to the fluoroscopy and digital fluoroscopy unit this fall. Okay. But you utilize a grid bias tube in order to create that machine gun burst of X-ray. Your anode assembly. So we talked about the cathode already. So there's two types of anode. The first type, the type that was invented first, the type that you see all the way back to the Crookes tube, is just a slab of metal. It's a stationary target, basically. Big chunk of metal. Now, typically, you're going to want to use copper for the base, all right? And then just put a little sheet metal square of tungsten for the focusing cup on the front of the copper. Okay. I can't remember when they figured out that a beveled target works better as far as preserving focal spot size and distributing heat. But beveled targets are standard for both types, for both a stationary anode X-ray tube, but also a rotating anode X-ray tube. Okay. The rotating anode, necessarily, you need the axle to be fused with a rotor that's part of an induction motor. Versus the stationary anode, you don't have a rotor and axle for your anode. Okay. All right, so your components are your anode, your stator, and your rotor for a rotating anode. Now the focal track is made out of, again, tungsten, but most of the anode is made out of molybdenum and graphite. The anode stem is usually made out of molybdenum. The molybdenum and the graphite connected to the back of the anode act as a heat sink for the tungsten focal spot. So both the molybdenum and the graphite will absorb and pull heat away from the tungsten, such that the focal spot doesn't overheat. Okay? So now your molybdenum wheel and your graphite is heated up. The graphite will give that heat back to the molybdenum. The molybdenum connects directly to the anode stem, which is also made out of molybdenum. Now, most of the time that is bolted on to the metal anode wheel. It's a bolt and screw thread assembly. And then the molybdenum stem is fused directly to the armature of the rotor, which is the outer shell or the outer cup of the rotor. The outer cup of the rotor is typically made out of copper such that it can rotate. Okay? Now, where does the positive charge come through? Well, the rotor axle is connected to the rectifier, and then by virtue of the ball bearings between the center axle of the rotor and the collar of the rotor, the collar is free to engage in rotational motion, but transfers the net positive charge from the anode stem through the bearings to the armature, the collar, then to the axle of the rotating anode, and then to the surface of the anode wheel, which includes the tungsten focal track. Okay. The difference between a focal track and a focal spot is the focal track is the entire bombardment area as throughout the exposure, but the focal spot is the theoretical bombardment area that exists right now. So an electron always hits in the same place, but not in the same place. It hits on the bottom of the anode, but that anode is always rotating, and so you end up with the bombardments spread out over the entire surface of the wheel. Okay. So, what is the improvement in design? Why do we use rotating anodes? Because they have greater heat capacity. So the heat capacity of a rotating anode, the focal spot size, that is the effective bombardment zone or the actual bombardment zone, the thickness of the wheel itself, how much mass of graphite does it have, how thick is the molybdenum layer. Those determine the capacity of heat that can absorb instantaneously. And then the speed of rotation is also proportional to spreading out the bombardments, and so more effectively distributing the heat, so it marginally increases heat capacity of the rotating anode. The stationary anode, the best setup is a water-cooled from inside stationary anode. So you connect the collar to the high voltage, but then you have a water chamber, maybe a circulating water chamber, inside the stationary anode, and that liquid pulls the heat away from the tungsten focal spot, the stationary tungsten focal spot. Okay. And we did see at least one schematic where the Coolidge tube had a water-cooled anode. So again, what material do we want? Well, it's tungsten rhenium alloy this time. Again, we're choosing tungsten because it has a high atomic number, high melting point, and high heat conductivity. So that means when the tungsten gets hot, it gives away its heat very rapidly, very efficiently. And so the heat transfer, remember this entire wheel is in a vacuum. And so convection is not available. The two methods of heat transfer are conduction back through the axle made of molybdenum, and then also infrared radiation coming off of the target anode, which also goes in all directions. All right, anode layering. Again, there's a graphite base or backing. The anode wheel itself is primarily molybdenum, and the focal track is primarily tungsten rhenium alloy. Okay? So you don't make the whole thing out of tungsten because tungsten is expensive. Molybdenum is got a similar heat capacity, but it's much cheaper than tungsten. Okay? So typically only the focal track of the anode is made out of tungsten. Okay, and all this is the diameter of the anode roughly, but effectively the anode's mass determines its heat capacity. It's a primary factor in determining the heat capacity of the X-ray tube. A 6-inch anode versus a 12-inch anode. The 12-inch anode, if everything else is the same, the 12-inch anode is going to have double the heat capacity of the 6-inch anode. Okay. If we use molybdenum as a target material, we're going to get lower energy X-ray photons out of a molybdenum target. Now, for X-rays of soft tissues like mammography, breast tissue, the molybdenum target is perfect for mammographic units. And so mammographic equipment has specialized X-ray tubes with different target material in the anode. They swap out the tungsten for molybdenum. They get a different characteristic X-ray of about 20 kVp or keV effectively. And they usually use a beryllium window. The beryllium window is, we can't use a conventional Pyrex window because it absorbs too many of the soft X-rays, and we need lower energy. So the X-ray techniques for mammography are somewhere around 20 to 25 kVp, as compared to in diagnostic imaging we start with 50 for a hand. Well, there's not supposed to be any bones in breast tissue. There are sometimes calcified granules and calcified deposits in breast tissue, but that's the exception, not the rule. Mostly it's just soft tissue. So we don't need as much penetration power, so we use reduced kVp in particular. And that's why we can get away with a different target material. Okay. We don't need 100 kVp, we only need about 20-25 to penetrate through a breast on average. Okay. The beryllium window is going to allow more of those low energy photons like we used in breast imaging to actually get through. It's not going to filter them out as efficiently as Pyrex glass or any sheet metal housing would. Okay, not housing, envelope. Okay, two different terms. Okay, fractional focal spot tube. All right, so the focal spots, the filament sizes for mammography are even smaller than the filament sizes for X-ray. And that's because we want high spatial resolution so we can see really, really tiny lucencies or findings, right? So we want to spot breast cancer tumors when they're very, very small. So we need a higher spatial resolution. That means we need a smaller focal spot size in our mammographic X-ray tube. Okay. The target area is the theoretical area where the electrons are actually intended to intersect the anode target. Okay. It's usually referred to as the focal spot. Okay. Occasionally referred to as the target, but that gets too generalized, and that some people misunderstand. And when you say anode target, they think you mean the entire anode rather than just the focal spot. So best practice is, if you mean focal spot, say focal spot. If you mean focal track, say focal track. If you mean the entire anode wheel, say anode. Okay? And that should eliminate the confusion. Now, as far as focus, I haven't heard that. Usually there is a modifier too. So I've heard focal point, which really doesn't exist. We can't create X-rays from a single point. Okay, the electrons are a stream, but there is a length and a width to that stream of electrons, even when it's focused. So getting all the electrons to hit the anode at one singular point in space on the wheel, it's impossible. The best we can do is about 0.3 millimeters by 0.3 millimeters, which is in the mammography tubes, which is about half of the small focal spot for a conventional X-ray tube. Okay. The track is only on rotating anodes. Okay. A stationary anode does not have a focal track. The track is what happens. It's the total area. If you take the focal spot at every point along the rotating anode, then you end up with the focal track. Okay, and so the focal track is circular. The focal spot is effectively a rectangle. Okay. It's understood, as far as our understanding of the geometry of the formation of the image, that the focal spot we treat it like it's a point source of X-ray emission, even though it's spread out over an area. It works out easier to explain certain things if you treat the X-ray source in an X-ray tube like a single point in space, even though that's not what's really happening. Makes some of the math easier on some of the calculations we have to do later. All right, so an important principle, if you're in my class, you're going to get the trig proof that I worked out. Okay, so you might see a right triangle. You might see two right triangles if you're clever, with two different hypotenuses and two different short sides. Okay, and so there's an A, B, and C prime triangle, and then there's an A, B, C triangle. And the difference is the magnitude of the target angle. Okay. Now in my trig proof, basically, as angle C prime AB changes to angle CAB, that top angle theta, as that gets smaller, both the actual focal spot and the effective focal spot also get smaller. So a steeper bevel makes for a smaller focal spot size. The larger the top angle on that right triangle, the larger both focal spot sizes are. Okay. Dual filament tubes sometimes have dual bevels, where the small filament has a very shallow bevel, a small tube angle, or target angle, but the large focal spot has a larger target angle. So I think we do have a dual bevel X-ray tube, X-ray target anode freestanding in the resource materials in the front of the classroom. So I'll be sure to show you that. Okay. For those of you taking my class, we will walk through the trig proof. You won't have to do the trig proof yourself, but I just want to show you how we get from trigonometry of these two right triangles to understanding that the hypotenuse expands when the target angle gets bigger, and the hypotenuse shrinks when the target angle gets smaller. Okay? That's not as intuitive as side CB grows to CB prime or C prime B. That one's a little bit more intuitive from the diagram, but the hypotenuse is also longer. Okay. All right. The actual focal spot is MA limited. Okay. And so if you want a small focal spot that gives you better detail, better spatial resolution, but you're limited as to your total tube current. You can't concentrate that many electron bombardments in that small of an area. Your typical small focal spot is about 0.6 of a millimeter by 0.6 of a millimeter. Okay, or is it? Hang on, let me look that up because that might be 0.6 centimeters. Let me look that up. I don't know if it's, and that's from Bouchon. They might not even have it here in the Adler book. Let me get to that. We're in chapter 5. See if he talks about what typical focal spot sizes are. Off focus, leakage, recharge, vacuum, envelope, rotor, heel effect. He does not, so just ignore that number. I'm not gonna, because I do think it's 0.6 millimeters for the small one and 1 millimeter for the large one. Okay. Yeah, he does give a range here on the bottom of page 86 in the Carroll book. Diagnostic tubes are available with focal spots of 0.1 all the way up to 3 millimeters. Okay. The greater the target angle, the larger the focal spot. And it does have, you'll find out in Mr. Shepard's class, he's going to teach you the focal spot formula versus penumbra. And so the edge blur varies. You get more, is a direct relationship to the focal spot size. Okay. So what's an inverse? The target angle is an inverse relationship with focal spot size. No, that's not true either. God bless it. Spatial resolution is an inverse relationship with focal spot size. Yeah. God bless. I am so sorry. I'll walk through that again because I don't want you to learn it the wrong way. All right. So spatial resolution decreases as focal spot size increases. Edge blur increases as focal spot size increases. So spatial resolution is inverse to edge blur, but also inverse to focal spot size. Edge blur and focal spot size have a direct relationship. As one increases, the other increases. Okay, I think I've got that straight now. Sorry about that. Terribly sorry. I know how frustrating that is when you're first learning it. So, okay, anode heel effect. Okay, so we have this rotating anode, and we have to have a heat sink in the base. Okay, so there's got to be a large mass in back of the target surface. And that has to extend down beyond the target surface, down in the direction of the patient. So because of that, there's matter there. All right. Now we're sending an X-ray beam in all directions, but part of the direction of the X-ray beam that's actually becomes the useful beam actually travels back through the heel. And that's the bottom posterior corner of the target anode. And so those X-ray photons traveling through the heel, they encounter molybdenum and graphite, which is carbon. There is some photoelectric effect going on, especially in the molybdenum. And so immediately part of the X-ray beam we generate at the focal spot is reabsorbed by photoelectric effect before it ever has a chance to leave the X-ray tube. It's reabsorbed by the anode wheel. So what happens is there are less photons per square centimeter on the anode side of the beam than there are on the cathode side of the beam. And so you can get an intensity variation of about a 45% swing, where the anode beam is thinner by about 45%. So let's say we had 100 photons per square centimeter coming out of the cathode side, you would only have 55 photons per square centimeter coming out of the anode side. Okay? This is called the anode heel effect. And so typically what we're instructed to do, at least in screen film days, was to put the thinnest part of the anatomy, if we had a tapering body part, underneath the anode of the X-ray tube. Okay? A good way to remember this was cat fat. So put the thicker anatomy, the fatter part of the pertinent anatomy underneath the cathode, the thinner part of the anatomy underneath the anode. Okay? Now, you will still need to know the anode heel effect on the registry exam. However, you don't have to worry about it if you're using a digital X-ray machine. You're going to learn in digital imaging that one of the pre-processing corrections is called flat fielding. And flat fielding is meant to handicap the pixels of your image receptor that are on the cathode side of the beam. And so basically it reduces the intensities at the cathode side of the remnant beam to compensate for heel effect and the inequality of intensity from the cathode to the anode of the X-ray beam. Okay. The only way to get rid of the heel effect is to get rid of the solid anode target. And if you get rid of the solid anode target, then you can't create X-rays. So it's a necessary component. And so we know that it's there. We compensate for it with the way that we position for tapering body parts or through digital software, but we're kind of stuck with the anode heel effect. Okay, moving on to our stator. Our stator is basically a series of electromagnets arranged in like a clock face, such that the opposite electromagnets, so if there's 6 electromagnets, which is a typical configuration, opposite electromagnets will create a north-south pole. And then as we cycle the power through the different pairs, we create a rotating magnetic field. Okay? The stator for the X-ray tube is actually outside of the envelope. It's still inside the tube housing, but it's not part of the X-ray tube itself. Okay? Stator failure. If the stator fails to create a rotating magnetic field, because motors do burn up, then you won't create rotational motion, and then you get bullet melt, or basically pit melting. Okay. If you have a cutting torch, um, if you've ever done any machining or welding and you've worked with a cutting torch, you might recognize that sore on the anode. Basically, you turned your X-ray machine into a cutting torch by having a non-rotating anode when it's intended to rotate. Now, a stationary anode is designed to take bombardments all in one location, and so you're not supposed to get a bullet melt. You can on a stationary anode if you overload it and ignore the heating chart. If it's a really old one that doesn't lock you out from the exposure, then you could effectively put a big melting hole burning through your stationary anode. But typically this manifests in a rotating anode that failed to rotate. Okay. Now basically what you've done here is you've ruined your X-ray tube at this point, because the focal spot every time this point passes, if you do get the anode rotating again, this anode will lose spatial resolution because there's a giant pit in the middle of the focal track at least one point on the anode. And we do have a pitted anode at the front of the classroom, and I'll show you that. I'll show you both a cracked anode and a pitted anode when we talk about tube damage. Now, our rotor is supposed to rotate, but is also supposed to supply the positive polarity coming off of our rectifier and our high voltage transformer. And so it's got two important jobs: convey the positive charges to the anode target, but also develop a rotating magnetic field in response to the induction by the stator, and then start spinning. Typically we want RPMs between 3,000 and 10,000 RPMs to effectively spread the heat out. Okay. The ball bearings are definitely the thinnest and least massive component, and so typically those are the ones that succumb to heat damage first. If it's not the actual target itself, then we can get ball bearing failure, which these are supposed to be spheres. If they get so hot that they start getting glowing orange, you can totally do this to your automobile too. Just forget to grease your axles and run it into the ground. The ball bearings, once they start glowing red and orange, they start to warp from spheroids into ellipsoids, and that's considered bearing failure. Your anode, your rotary axle will start to wobble, and your entire anode wheel will start to wobble. When that happens, your focal spot size effectively gets radically large with anode wobble, and so you've ruined your X-ray tube at that point. And so part of the heat capacity and allowing the anode to cool off is to prevent rotor bearing warp. We also want to prevent the pitting to the anode wheel itself, but rotor bearing warp is far more common a concern. Okay. So typically they come in two versions: standard speed, which is a little bit over 3,000 RPMs, and then high speed, that's 10,000 to 12,000 RPMs. Okay. High speed rotors typically have to be bulkier and have more mass and thicker anode stems, because you do get a gyroscopic effect and a conservation of angular momentum, and they have to be machined and precisely engineered so there is no precession, no wobble in the rotation. Okay. All right, so your X-ray tube should whine a little bit, like it says, like your automobile, more like your vacuum cleaner. Your vacuum cleaner has a whining sound to it, kind of sounds like a jet turbine. That's the motor of your vacuum cleaner. Okay. When the rotor bearings start warping, then you get this gravelly crunching sound laced in with the whine. Okay. So any unusual sounds, if it doesn't sound like a constant tone whine, kind of like a whir sound, if there's any variance to that, or if there's any gravelly sound, that might be the rotor and the stator are about to fail. Okay. The stator is either about to burn up or the rotor bearings are warped. Those are the two most common errors with the induction motor. All right, our envelope, heat tolerant Pyrex glass. You know Pyrex glass, invented in Corning, New York. I totally took a tour of the Corning Glass Museum during, I think it was middle school, because I grew up maybe an hour and a half from Corning, New York. And so I think it was 8th grade science class. We took a field trip to Corning so we can all learn about the history of glass making. And they did show us what was different about making Pyrex. Basically, they superheat the glass to remove the impurities. It's pure silicon dioxide. Usually, most regular glass has a little bit of carbon or iron in it, or maybe even some copper. Colored glass or stained glass, usually they're adding some kind of metal salt to the glass to create the stain during the heating process. Okay. So if you want blue glass, you're going to add copper salt. If you want green glass, you're going to add a mixture of some copper salt and what is it that turns yellow? Maybe like an aluminum salt. Okay, but different metals will give you different colors of glass. Okay, Pyrex glass is always clear because it's always pure silicon dioxide. And when it's allowed to cool down really slowly, it forms a uniform matrix with very little flaws or defects. Okay? And that allows it to distribute the heat through the glass fairly uniformly. It's when the molecular lattice of glass has impurities or defects or even air bubbles in it that it doesn't heat uniformly. An air bubble in particular would be a hot spot because the air trapped inside the glass would effectively cool down that region of the glass. And so that would be a cold spot relative to the rest of the glass that doesn't have air, would be hot, and then you get a temperature differential across the glass matrix. In most circumstances, the temperature differential isn't significant enough. Like your window pane glass, that has air bubbles all through it and impurities all through it, but it doesn't get hot enough. Okay. But sticking it in an oven, if you take window pane glass and you throw it in your oven and heat it up to about 400 degrees, then it is going to have uneven heat distribution, and that's actually going to cause physical stress across the molecular matrix. That physical stress builds up until the glass cracks. Okay. You can tell the difference between Pyrex and cheap glass bakeware by putting it in your oven and heating it up to 400 degrees, 300 degrees. And now the glass will explode if it's cheap, and you do this. Next step, take it out and immediately put it under the cold water faucet. Okay? that creates a huge temperature differential from the internal temperature of the glass that is 300 degrees, and now the top surface is the temperature is plummeting rapidly because the cold water is pulling away the heat rapidly. You get a huge temperature differential across the matrix, a crack forms, and you can get some cheap glassware, especially if it's got a lot of air bubbles in it, to literally explode in your sink. Okay, so Pyrex glass is basically oven safe, and it resists the urge to fracture and explode. Okay, now I still wouldn't run it under cold water immediately after taking it out of the oven, but it's less likely to crack and shatter. It's more heat tolerant than other forms of glass. Okay, and so that makes it the natural choice for X-ray tube design. Now they've figured out that they don't need a glass envelope somewhere in the last 30 years. They can actually use sheet metal, okay, rather than a glass envelope, and the sheet metal can act as an X-ray filter, so you can actually increase X-ray filtration by making your tube envelope out of sheet metal. And so modern tubes made out of sheet metal, and I think per square meter, per square inch, sheet metal is probably cheaper to make than Pyrex is. Okay, right? The tube window is the area of the intended exit of the X-ray beam. Now remember, the X-ray beam actually spreads in all directions, okay? But the tube window is facing toward the collimator box and the aperture to the tube housing. That's what's special about the tube window. In glass envelopes, the tube window was the thinnest portion of the glass envelope. I don't know how they do it with the modern sheet metal envelopes. Okay, whether they pound it thinner right there at the tube window or they leave it the same thickness all the way around. Okay. Vacuum, near perfect and critical to efficient X-ray production. Okay, so you can have inefficient X-ray production with a low pressure, very low pressure X-ray tube. Remember, the Crookes tube was a low pressure system rather than a perfect vacuum system. But in modern engineering, we can effectively create a perfect vacuum X-ray tube. Okay? But that means as soon as that vacuum is violated, as soon as the envelope is compromised, the X-ray tube is immediately gassy and worthless. Okay? And that is the number one cause of tube failure, is a gassy X-ray tube by arcing. Okay? So here we have a picture of the X-ray tube inside the tube housing. We can see the connectors for the high voltage wires coming in from the back of the X-ray tube, or the top of the X-ray tube, if you will. The stator is completely within the tube housing. The tube housing is capped on either side, so it is a sealed container. There are ceramic liners around the high voltage cables until you get to the insulating oil tank. And so the green area is filled with what's called dielectric oil. Okay, it is the same oil that's in the transformer buckets. So those garbage can looking things hanging off the telephone poles, yeah, that's totally a step down transformer. Okay, transformers and X-ray tubes are submerged under insulating oil. Dielectric means insulating. Okay, dielectric, it means an insulator that also grounds. Okay, that's an important principle with the insulating oil, because it also grounds out the X-ray tube. Okay, and the high voltage cables. Okay, but it effectively insulates the cathode side wire from the anode side wire, but also grounds them out. It's a funny material. Okay, it's also a known carcinogen. Okay, and so I do have to tell on bad clinical practice. I don't know the specific technologists involved, but they had a leaking X-ray tube that was dripping insulating oil, and they told my students to keep taking X-rays. No, that's a known carcinogen. Shut your dang room down and get it fixed. Okay. They were having so when they laid the patient down on the table, hopefully it wasn't dripping carcinogenic oil on the patient themselves, but they had to change the linens out more frequently because they found if they left linen on the table, it would have an oil stain on it by the time they got the next patient in there. So they couldn't actually dress the table with linens until the moment in time and they had to mop up a little puddle of oil and quickly dress the table with linens. Or, maybe shut down the room because that's a known carcinogen. So anyway, that's the end of my shaming lecture about one of my clinical sites, and hopefully they've learned their lesson, and hopefully you, as a practitioner going forward into your career after you finish this and all your other courses, will have the wisdom to say, "Oh, hell no," and refuse to work on a leaking X-ray machine. Okay? If the insulating oil is leaking, one of the jobs of the insulating oil is to effectively cool down the tube. So if the insulating oil is leaking, how is it maintaining its volume? If it's not maintaining its volume, that means there's an air bubble inside the tube housing. That means the tube is not cooling down effectively. And so the other fundamental flaw, other than exposing your patients and your technologists to a known carcinogen, is you're running an X-ray tube when its heat dispersion mechanism is not operating as efficiently as it ought to. Okay. Water cooling in high-end tube designs. That's going to be your CT scanner primarily. Okay. So the CT scanner has a refrigerator coil, water-based. It probably is the same refrigerant as you find in the radiator of your car. So that's ethylene glycol, that's antifreeze. Okay. But that's ethylene glycol diluted with 1-to-1 with water. So it says water cooled here, but it's probably antifreeze cooled. And it's a closed plumbing pipe network with a water pump. And so cold water comes in, pulls heat away from the tube housing, and then cycles back down to the reservoir tank. And the reservoir tank radiates heat. The water in the reservoir tank cools off and then runs back through the pump, and then the cold water and antifreeze mix comes back to the tube to pull more heat away from the tube. Exactly how the radiator works in your car. Okay, and keeps the engine cool. Okay. Off-focus radiation. So the intent is for that electron stream to remain kind of like a rifle shot, where it's pointing only at one specific spot on the anode target, and all the electrons theoretically are supposed to bombard inside this little tiny target region. Okay? But that's not what happens. What happens is electrons are quantum objects, and so although we like to think of them as particles, they occasionally according to probability, they do screwy things. One of the screwy things they do is they don't take the shortest path, they go to the entire anode wheel. They go to the tube housing. Okay? They go basically everywhere except for staying at the filament. Okay? So they hit all over the anode. Some of them hit the axle. Some of them hit the armature collar for the rotor. Yeah, electrons. Well, that's not a straight line path. How do they do that? They're quantum objects. That's how they do that. So as many as 25% of the electrons we send out of the space charge don't hit the intended target. And we call this stuff off-focus radiation. Okay? Because most of the X-ray is coming from the target, but as much as 25% of the X-ray is coming from random places within the X-ray tube. And so these X-ray photons, like their electrons that spawned them, are heading off in unintended directions. And so we try to control like the escape route of the X-ray beam, but we're gambling on that the X-rays started from the focal spot. And so our apertures and our collimators are aligned to the focal spot. And so we can rein in the size of the beam from the photons that are created the right way. Any of the off-focus photons, the aperture and the collimator blades are not lined up appropriately to rein those in, and so we do get some off-focus radiation heading out of the X-ray tube and outside of the collimated field. Okay. If enough off-focus radiation hits the image receptor, it can produce some actual deposition of a significant amount of photons outside the collimation on our image receptor, and then that can be misinterpreted by our software into fooling the software into believing that that's part of the anatomy that we want to optimally display. And so off-focus radiation can become a problem. Okay. Now the way that you limit off-focus radiation is to just collimate down as much as you can. Okay. Smaller apertures, smaller fields of view, smaller collimated fields limit the effect of off-focus radiation. Larger fields include more off-focus radiation. All right. So that's the piece parts of our X-ray tube, our line focus principle, our anode heel, our bevel to our anode target. The reason that we have target rotation is for more heat capacity. The targets typically rotate somewhere between 3,000 RPM and 10 to 12,000 RPM. You're going to find 10,000, 12,000 RPM on your CT machines and in your fluoroscopy suites. Most of your conventional X-ray machines are going to be 3,000 RPMs. Your portable X-ray machines are going to be 3,000 RPMs. Okay. We again talked a little bit about how damage manifests in the X-ray machine. Rotor bearing warp, pitting or cracking of the anode, and off-focus radiation and arcing, and then you compromise the vacuum. Okay. We talked about what was necessary for X-ray production. That is a source of electrons, a target for them to slam into, and kilovoltage to accelerate them into the target. All the other components, the focusing cup, the beveled anode, the rotating anode, those are all efficiency improvements. The total vacuum is an efficiency improvement. Okay. So by an efficiency improvement, that means you can still make a crude X-ray tube. Remember, the first X-ray tube was a Crookes tube, and it was only partially vacuum evacuated. It had a cold cathode, no focusing cup, right, and no rotating anode. Okay, and they still made X-rays with it. So that's the difference between necessary and efficiency improvements. Okay, your modern X-ray tube, all the components are present in the modern X-ray tube. Right? Remember the grid biased focusing cup. It alternates polarity between positive and negative charge, such that you get a machine gun like bolus, so tiny little bursts of X-ray pulses at high frequency, and typically that frequency matches the data dump frequency of your digital detector on your fluoroscope, and so you get 30 frames per second motion picture. It's very much like video games. That's how video games do motion picture. It's actually 30 still frame, greater than 30 still frames per second, with subtle little changes in between the frames, creates the illusion of a motion picture. Okay, and so with that grid bias design and pulse fluoroscopy, we can significantly save dose with digital fluoroscopy. Okay. The line focus principle is based on the principles of trigonometry, such that the small side of the triangle can remain small, but the hypotenuse can absorb the bombardments and can be the bombardment surface for the electrons. And so with a target angle of somewhere, usually the target angles range, think down, small is like 5 degrees all the way up to 20 degrees. With a target angle, you can spread out electron bombardments over the hypotenuse of the triangle, while effectively the X-rays appear like they're the small side of the triangle, that is the opposite side of the triangle. Okay. And for my students, I'll hand out you won't have to know the trig proof, but I've done the trig proof for the line focus principle, and I'll walk you through the line focus principle. It's basically, if you understand the Pythagorean theorem, and then we also invoke SOHCAHTOA. I don't know if you don't have to know trigonometry. I could teach you SOHCAHTOA while I'm teaching you the trig proof for the line focus principle. And it basically, oh yeah, that makes sense. As this angle gets bigger, both the opposite side to the angle gets bigger, but also the hypotenuse gets bigger. And that's effectively what the line focus principle takes advantage of. Okay. We went back through the piece parts of the induction motor. And then we also described the construction of the envelope. The protective housing is lead steel alloy. I didn't get into that, but we'll get into that in radiation protection radiobiology, as far as why does that have to be a lead steel alloy of a certain thickness. It's to stop all the radiation that is not heading down through the collimator. So, well, that's the end of this one. I think I've got one more, and then we're finished up with the physics series. So hope you've enjoyed listening. Take care.